аудитория англоязычная, вообще говоря, да?
Ну, да, частично англоязычная,
Хорошо.
так что мы...
Ну да, но все равно это на английском, так что
Ага.
проблем не должно быть. Okay, I think it's already the time to start.
Okay.
I
So I ask the participants to switch off microphones if you do not need them.
Exactly.
Okay.
I hope I don't need to show up. It's sufficient to be only... my voice is sufficient, right? Okay, so today we'll talk about Riemannian Cartan-Lie algebroids, groupoids, and curved Yang-Mills-Higgs models as motivation for them. And this kind of interplay between Lie algebroids, groupoids, geometry of PDEs, and gauge theories. And I hope I will try to make it clear, although there are some details which probably I will not be able to explain very good, but everyone will be able to see the presentation file afterwards. Okay, the plan of the talk is the following. So first of all, I will talk about connections and metrics on Lie algebroids. And I will start with Bott sequence and linear connections in terms of Bott sequences. Then I will explain what is a Lie algebroid. I am pretty sure that you heard this many times at this seminar, but I will do this briefly for the purpose of the talk. Then I will say what are the connections on Lie algebroids and how they are related to the first two, and in particular to Bott sequences. Then I explain what are the Cartan-Lie algebroids, and they're really related to Cartan structures. Then I will say how this can be connected to metrics, in particular to Riemannian metrics on the base manifold. The second part will be about Riemannian Cartan-Lie groupoids. So this is the integration picture, the exponentiation of Lie algebroids is a Lie groupoid. If we integrate all the previous structures, we'll get some particular kind of Lie groupoids. And these are related to jet groupoids, Riemannian groupoids. And the last one, which I will probably, I will skip many details here, will be the motivation, actually how we came to that. Because there are communities who came to Cartan-Lie algebroids, groupoids, and all similar structures, multiplicative structures from the purposes of Lie equations. But we did this from the opposite side. We tried to construct some gauge theory, which generalizes Yang-Mills-Higgs theory, and then we discovered all these structures as the background geometry. Okay, so the first about Bott sequences and linear connections. Again, I'm pretty sure that it's kind of common knowledge, but let me briefly repeat this. So suppose we have a vector bundle E over a manifold M. Let's consider a short exact sequence of differential operators. So dk pi1, pi is a vector bundle. Dk pi1 means differential operator, the bundle of differential operators of order k equals from sections of this bundle to functions. So the trivial bundle of rank 1. The symbol is the principal symbol. So this is the right non-zero arrow. And the left one is the natural inclusion of differential operators of order k minus 1 into differential operators of order k. So the notations are below. And this is a well-known sequence known from the theory of PDEs. If we try to dualize it, we should first notice that dk differential operators of order k, the bundle of differential operators of order k acting from sections of pi to functions is due to k jets of sections of pi. And then if you dualize the exact sequence for the symbolic exact sequence, we will obtain another exact sequence, which is called the Bott sequence. And instead of differential operators, we write jets. And now, instead of the embedding of differential operators for the k minus 1 into order k, we have a projection from jets of order k to k minus 1. This is for the forgetful operator. And in the kernel, we always have sk of t star m cross tensor product E. This appeared in the paper of Bott in 1963 about Spencer resolution. At least I know this was the first reference. In particular, if k equals to 1, then this exact sequence looks as follows. So this is 0 to t star m tensor e to first jets of e to 0. I slightly changed the notations because instead of pi, I write here e for some for simplicity for the next notations. And in particular, if you try to write the embedding of t star m cross e into first jets, the formula looks as follows. So f dh cross s is embedded precisely like that. Just for some formula which is sometimes useful for computations. In these notations, jet J1 of S is the first jet prolongation of S. Then every connection nabla on E uniquely corresponds to a splitting of this exact sequence. So to a map from E to J1 of E such that being composed with the projection gives the identity on E. And the precise formula looks as follows. So the embedding sigma x on every section S of E as follows. So the first jet prolongation of S plus nabla S. Actually, plus here is some sign convention. The idea that the first jet prolongation is a differential operators, universal differential operators of order 1. So it differentiates coefficients of sections. But nabla is doing the same. If you take the sum with the right sign convention, then it turns out to be a 5/s linear operator. So it's a bundle map. And then it's easy to see that if you compose this with the projection of first jets to E, we obtain the identity map. And nabla S is identified with one forms on M twisted by E. So it's, as we know, this is in the kernel of the short exact sequence of both of order 1. So again, what is important that connections are in one-to-one correspondence with splitting of this exact sequence. Now, Lie algebroids. Lie algebroids is a generalization of Lie algebras and the tangent bundle at the same time. So both are particular examples, so it's kind of boundary examples of that. So the definition is the following. So a Lie algebroid, E, rho, and the brackets, the data over M. First of all, it's a vector bundle E over M together with a Lie bracket of sections. And the bundle map from E to Tm, which is called the anchor, such that the following properties are holding. So actually, we have the properties of the Lie bracket of vector fields, except the Lie derivative of function along a section of E is not well defined, but it's defined whenever we have rho, the anchor map. So the map from E to Tm. And then combined with rho, it gives the right definition of a Lie algebroid. So as I said, the examples are, the first example is G, a Lie algebra, and it's regarded as a vector bundle over a point. And then the anchor map, of course, is 0, and this is just the Lie algebra structure. The second example, which is, again, one critical example, is Tm. It's called the standard Lie algebroid. And of course, if you write E equals to Tm and the anchor map equals to the identity in Tm, we obtain all the above properties. They will be automatically satisfied, of course. Another example, suppose we have a principal H bundle, where H is a Lie group over a manifold M, P over M. And let's consider P quotient out by H. And it turns out to be vector bundle over M. It's not Tm, right? It's bigger. And then this is a Lie algebroid over M, which is called the IT algebroid or algebroid of infinitesimal symmetries of P. So the anchor map in this case is surjective. So it's called a transitive Lie algebroid. The anchor map rho is surjective. And in the kernel, we have the bundle whose fiber is the Lie algebra H of H. And one more example, which is very useful. If E equals to G cross M, where G is a Lie algebra, it's called an action Lie algebroid. And here the data is the following. G is a Lie algebra which acts on a manifold M. The anchor map is a prolongation of the map from sections of elements of E to vector fields. And now we extend this by use of C infinity M linearity. And the Lie bracket also is the canonical extension of the Lie bracket on G, where we use also the Leibniz rule. So for sections which are just constant elements of G, this is just the bracket of Lie elements of Lie algebra. And whenever we have coefficients which are functions on M, then sections are acting by the anchor map. And the anchor map is precisely the infinitesimal action of sections on M. So it's a Lie algebroid. It's called an action Lie algebroid, one of good examples. So Lie algebroids, it's known that it was invented by Jean Pradines, who was a student of Erisman, and Erisman was a student of Cartan. Actually, all this, if I understand correctly, all this machinery was invented to understand the ideas of Cartan. And then it moved into some side direction. So the theory of Lie algebroids started developing itself. And then at some moment already, maybe 10 years ago, 15 years ago, it came back to the Cartan structures. And then now people related this to the papers to the works of Cartan. One more definition. So it's known that Lie algebra may act on a vector space. And then we have a representation. So given a Lie algebra intervector bundle with the same base, an E connection on V is defined at the same way as a usual connection, except we differentiate not along sections, which are now elements of gamma E, but along rho of S. So if we just define this covariant derivative in the same way as usual covariant derivative, but except actions of vector fields, we have actions of rho of S. S is a section of E. Then whenever we have a connection on E connection on V, sorry, view it as a vector bundle, we can define, connection on E, where E is viewed as a vector bundle. Then we can define just the same way as of a connection, TM connection on TM, we can define the torsion, which says how the difference between nabla S is prime and nabla S prime and S, how this difference is different to the bracket, with the bracket. So this, the torsion is now is a tensor structure, which is obviously take values on lambda 2 E star cross E. Like usual torsion is a two-form twisted by TM. For instance, in particular, suppose nabla is a vector bundle connection on E in the usual sense, so it's a TM connection. Then we can define a E connection out of that by the formula. So nabla E S applied to S prime is the same as nabla rho S S prime. It's one of the simplest ways how to define it. Now let's come back to the both sequence and connections. Now we relate all this. So suppose E rho and the bracket is a Lie algebroid over M. Then the bundle of k jets of sections, global sections of E is an Lie algebroid itself, and the bracket is defined as follows. So we require that the bracket, first of all, it commutes with the prolongation. So the bracket of JKS and JKS S prime is JK of S and S prime for all sections S and S prime of E. And the anchor map just is the composition of the anchor map with the forgetful map. So rho of JKS equals to the rho of S. There's some nice explanation how it appears. I will say just a few words later about that. So the Lie algebroids are in one-to-one correspondence with certain differential graded.
Lёsh, I'm sorry.
Okay.
But sections of the k jet bundle are not exhausted by jets of sections. What to do with sections like JKS? They are linear combinations of jets. So how to define?
No. I want to say, I understand. Of course, you are right. I want to say that if E was a nonlinear bundle, this wouldn't be the jet bundle of local sections. But now we can say that it's a jet bundle of global sections. Everything is generated, as you said. Of course, it's a linear combination, but they are generated by jets of global sections.
They are generated, yes, but what to do with the bracket?
Yeah, with the bracket, as I said, so the bracket of jet prolongation of the bracket. And if we want to extend this to linear combination, we use the anchor map as usual. So that
use the anchor map.
Yeah, the Leibniz rule. Yes, exactly. Okay. And this actually, there is a nice explanation, which once I discovered, I don't know if it was known before, that there's a paper. Just if someone is not interested, that you can skip at this. But there was a paper in 1997 of Weintraub who related Lie algebroids in one-to-one with certain type of differential graded manifolds. So they're manifolds, graded manifolds of degree 1 with a Q field, homological vector field. And then jet K corresponds exactly to K prolongation of this vector field to the space of K jets. So that's just a very simple explanation in one line how to get it in terms of supergeometry. But okay, let me continue. So now I'm doing everything in terms of usual geometry, just skipping this super language now. For now. So the example, in particular, if it consider J1 of Tm of the standard Lie algebroid, then it becomes isomorphic to the AT algebroid of the principal bundle of tangent frames. So I already said what is an AT algebroid, and J1 is in one-to-one with it. So it's sufficiently big for that. I will later say how this acts on vector fields in particular. Now the Bott sequence, which was at the very beginning, is not a short exact sequence of vector bundles, but also short exact sequence of Lie algebroids. So it respects, in this case, it's easy to see what is a morphism of Lie algebroids, just morphism of brackets, because everything else is preserved. If the Lie algebroids over different bases, then it's more complicated to say what is a morphism. But here it's easy, it's just some bundle map which respects the bracket of sections. Then suppose E is a Lie algebroid, which is involved here. Let's take a short exact sequence corresponding to K equals to 1. And as we already seen, a vector bundle corresponds to, vector bundle connection on E corresponds to an splitting of this short exact sequence. So it's a map sigma from E to J1E, which splits the short exact sequence. And now we can ask whether it respects the bracket of sections or not, whether it's a morphism of Lie algebroids. And then the abstraction for being a morphism is usually it's a tensor, which is defined as follows. So S big of S small s prime equals to the difference between sigma s prime, the bracket between 2 minus sigma s prime. It's like a sort of curvature, but it's not the curvature of the connection. It's another type of curvature in this case. So now it's easy to see that rho of S composed with S equals to 0. So it means S can be identified with a section of lambda 2 E star cross E cross T star M. So it's a tensor. And whenever this tensor vanishes, then we have a morphism of Lie algebroids. Then there's some formula which at least once used for computations, how to write this abstraction in terms of Lie derivatives lots of sections of Lie algebroid and the connection. Nabla, so the formula is kind of simple for that. And there's another formula which is even shorter, much shorter, and this formula first appeared in when we computed the gauge theory, and then S equals to the following. So this is number of T, the torsion which was invented before, plus 2 the alternation of rho contracted with the curvature of sigma. So actually there are not too many ways how to contract them. So the only reasonable way, we obtain some element in E star cross E cross T star M cross E star cross E star cross T star M cross E, and then we should alternate with respect to E star, and we'll get an element of lambda 2 E star cross T star cross E, and nabla of T is exactly of this form, and then S can be written like this. It's a very short description, which is sometimes nice in computations. Okay, and now what can we do with this data? So now we come to another notation. So E a Lie algebroid together with a connection nabla is called Cartan-Lie algebroid over M, if E is a Lie algebroid, nabla is a connection, and the induced splitting is a Lie algebroid morphism, or in other words, the abstraction S vanishes, S equals to 0. Well, actually, this was, of course, it was inspired by theory of Lie equations. But first, this notation appeared in papers of Bloom from 2004 2005 about geometric structures and deformed infinitesimal symmetry. So, of course, he knew how this appeared, the origin of that. So, let me give you a few examples of them, of this structure. So, in particular, if E is an action Lie algebroid, so it's M cross G, where G is a Lie algebra acting on M, as I defined. Then there is canonical flat connection. Flat means the curvature equals to 0, which is defined such that constant elements of G, being considered as sections of E, which is M cross G, are exactly flat sections with respect to this connection. So it's a unique connection defined like that. And this connection is, one can easily check that this connection is a Cartan connection. So it's an example of a Cartan-Lie algebroid where the connection is flat. In the opposite way, if the connection is flat, then at least it's locally an action Lie algebroid, and globally depends on the topology of manifold, of course, and the bundle. And at least locally, it's an action Lie algebroid. Another, suppose E is a bundle of Lie algebras, which means that the anchor map equals to 0. So just we have only the kernel of the anchor map, which is a bundle of Lie algebras. And then nabla on E is compatible with this structure on E. So it's a Cartan connection if and only if it preserves the fiber-wise Lie bracket. So in particular, it means that all Lie algebras are the same, are conjugated. Now, if E is the standard Lie algebroid, the connection on E is compatible, or it's a Cartan connection, if and only if the dual connection is flat. Okay, the dual connection, sorry, I did not define what is the dual connection. Maybe, yes, probably later. So, however, any torsion-free connection gives rise to a compatible connection on Jet1 of Tm. So, suppose we have a Lie algebroid which acts on a vector bundle. Then we say that E is acting on, so suppose we have a Lie algebroid and together with the E connection on vector bundle, then we say that E is acting on V if this connection is flat or its curvature is 0. So it's a generalization. In other words, there is a representation of E on sections of P, so it's a generalization. Well, so that's some naive way of thinking about action, which is not very correct. So suppose we have a vector field X and some tensor field on a manifold. Then, of course, the Lie bracket, the Lie derivative is along X will respect the bracket, but this will be not C-infinity linear with respect to vector fields unless the tensor fields are just functions. Otherwise, it will also differentiate coefficients of a vector field. And then, if you say what does it mean? It means that in fact we have a representation of not Tm but Jet1 of Tm. So such that Jet1, the first prolongation of X, acts on tensor fields exactly by the Lie derivative, and then we extend by C-infinity linearity. So in more general, in the same way, we can say that the Lie algebroid is so Jet1 of E is acting on the tensor powers of E and E star. So there are simple formulas how it acts. So it's a generalization of a Lie derivative, and then in fact we have a representation not of E on tensor powers of E and E star, but of Jet1 of E, the first jet prolongation. And then so whenever we have a connection on E, then we can compose the action of Jet1 on a vector bundle V together with this connection, and then we have, so in this case V is either Tm or E itself, and then if the connection is a Cartan connection, then both maps are So in one map, so the splitting given the connection is the algebroid morphism, and another one is a representation of J1 on a vector bundle V. And this means that we obtain a representation of E, either on E itself or in Tm. So there are two types of representations, and their formulas are written like that, just written below. I denote this nabla alpha S and S prime, and nabla tau. Alpha means on a Lie algebroid, and tau means tangent. And whenever a Lie algebroid, whenever a connection nabla on a Lie algebroid is a Cartan connection, then these are actions of the Lie algebroid on the Lie algebroid itself as a vector, be it considered as a vector bundle, and Tm. And then, it's easy to see the anchor map interchange between nabla tau and nabla alpha. Now, how relate everything to Riemannian matrix on a base, and then actually was another paper. Actually, all this is a sequence of series of joint works with Thomas Strobel, and this was another paper with him, where we related Riemannian matrix, certain type of algebroids on Riemannian manifolds with gauging of the standard sigma model. But let me talk about mathematics now only. So suppose E is a Lie algebroid over Riemannian manifold Mg. Nabla is a vector bundle connection on E. Then E nabla is called a Lie killing the algebroid. We do not require that nabla is Cartan. It's nothing to do at the moment with the Lie algebroid structures. Then so the pair E and nabla is called a killing the algebroid if the following property is holding. So the tau connection applied to G equals to 0. Then, if this happens, then the following formula is holding. And now you see that if S, just in the formula below, if S is flat with respect to nabla, then the section rho of S gives a killing vector field on a manifold. But the definition is more general. So in particular, Mg may not possess any killing vector, but this can be still the structure of this sort over it. So in the above formula, if every flat section S on E gives an infinitesimal symmetry killing vector field. And this gives an example, just the generalization of the above statement. So suppose we have a Lie algebra which acts on Mg by infinitesimal isometries, then an action Lie algebroid with the standard flat connection is a killing Lie algebroid. But of course, it's just another way of saying about killing vector fields, but it's not, of course, it's not all what we can get out of this. Now I will show how this related to Riemannian submersions and later to Riemannian foliations. Suppose let me recall what is a Riemannian submersion first. Suppose Mg and Bh are Riemannian manifolds, and pi from M to B is surjective submersion. Then pi is called a Riemannian submersion if d pi maps isometrically the orthogonal complement to the vertical vectors to the tangent of B, or equivalently dp star, which acts from T star B to T star M, is an isometric embedding for each Z. Suppose we have a Riemannian submersion. Now let's take E as the kernel of d pi together with the connection, which is the orthogonal projection of the Levi-Civita connection onto E. Then it's a killing the algebroid. It's just an easy example. And now we can generalize it. So there's a general notion of Riemannian foliation, which generalizes the usual Riemannian submersion. And this definition, due to Molina, was written in the old book, and I guess even in the 80s. Suppose we have a generally singular foliation of a Riemannian manifold by leaves. So the Riemannian manifold M with the metric G, and it's called, the foliation is called Riemannian if every geodesic which starts in the direction perpendicular to one leaf remain perpendicular to other, or orthogonal to all other leaves. The velocity of which at some point is orthogonal to the corresponding leaf, then it will remain orthogonal to other leaves. So this is a geometric definition of Riemannian falations, and here we do not require that this falation is obtained in a certain way. So just any falated manifold with such a property is called Riemannian falation. And okay, it's easy to see that this is a generalization just of falation by parallel planes of a Euclidean space. Of course, if you have a line which is perpendicular orthogonal to one of the planes, it will be orthogonal to other planes. And this is the generalization of that fact. So if you have a Lie algebroid E over M, then it defines a singular falation of M. Simply, this falation is generated by rho of E, the image of the anchor map. So given that rho respects the bracket of sections, it will be closed. It will be an involutive distribution of Tm on Tm. And then there's a theorem that every involutive distribution, which is finally generated, gives rise to an integrable falation. Now, so we have a falation. Now, suppose we have a killing the algebroid with the properties above, then the obtained falation is Riemannian. And this is non-trivial result. Actually, in the opposite direction, it's not true. So later we found it. Actually, Thomas with his student, he found an example of a singular falation which is not of that sort. But in fact, it covers a lot of them. We just discovered this structure looking at some of Gaussian of sigma models. Now, okay, let me now say maybe in few words, or maybe I will skip this because it's probably it's not that crucial. I will come back if needed. So there's some nice structure. So let's consider the category whose objects are anchored bundles. So these bundles with some map from the bundle to Tm, with a bundle map from this bundle to Tm. With connections and morphism, the connection preserving bundles, and C-Li-M is the category of Cartan-Lie algebroids. So the objects are Cartan-Lie algebroids, and morphisms are maps, bundle maps, which preserve the connections. Then there is a natural forgetful functor from one to another one, which simply forgets about the Lie algebroid structures. Then this functor admits a left adjoint functor. And this construction is called a free Cartan-Lie algebroid. And left adjoint means that so the homomorphisms in the category of C-Lie Cartan-Lie algebroids over M from this free E to E prime is the same as homomorphisms now in the category of anchored bundles from E to E prime for every Cartan-Lie algebroid. So okay, the same theorem which is originally invented by Kapranov, he constructed free Lie algebroids in the same way as left adjoint functor. We did the same for Cartan-Lie algebroids, saying that every connection on an anchored vector bundle can be uniquely extended to a Cartan connection on a free Lie algebroid. But actually, the free Lie algebroid is infinite dimensional Lie algebroid. It's not easy to work with this. And in particular, if the original anchor bundle was compatible with the Riemannian metric, then the obtained infinite dimensional free Cartan-Lie algebroids will be a killing Lie algebroid respecting the same metric. But as I said, so that's our theorem with stones. But as I said, it's not easy to work with infinite dimensional Lie algebroids. But for instance, for infinite dimensional Lie algebroids, this theorem that every involutive falation every involutive distribution generated by such an algebroid is necessarily integrable. It's not true. Like for instance, we know that the Cartan distribution on infinite jets is not integrable. This kind of certain example which always may appear when we are in infinite dimensional setting. Now let me explain how this is related to what is an exponentiation, what is the integrated picture of all this. So we know this the Lie theorem that every Lie algebra can be integrated to a Lie group in finite dimensional Lie algebra to simply connected Lie group. It's then simply connected. The result is unique. There's also a similar theorem for Lie algebroids due to Kraenig-Fernandez, that under certain conditions, certain topological conditions, certain topological in some sense, a Lie algebroid can be integrated to a Lie groupoid. So a Lie groupoid is a generalization of a group. So it's a category such that all arrows are invertible and all structure maps are smooth maps. So there's some manifold G with two maps, the source and the target, how it's written in the picture, the target and the source. Both are surjective submersions. M is G0, the set of objects. G itself is the set of arrows. And all the structure maps, the partial G cross G over M, the map from the fibrate product to G. So we cannot compose all arrows, but only those arrows for which one the target equals to the source of another one. The inverse and the identity all are smooth maps. This is the requirement for Lie groupoid being for groupoid being a Lie groupoid. We have such a structure. We can look. So we have two submersions. First the target and second the source. So the same base manifold, and we can look at a bundle of vertical vectors with respect to both S and T. So I denote this as VS. So they're vertical, which are parallel to S fibers, and VT are parallel to T fibers. So the picture. It's easy to see how it looks in the picture. Then, given a Lie groupoid, we can construct a Lie algebroid out of it as follows. So we take all vector fields on G which are tangent to T fibers, so that T tangent is also the left invariant with respect to the multiplication. Actually, G does not, the groupoid itself does not act on all vectors. So that's, I will show that for that we need some additional structure in contrast to Lie groups, for instance. But one can see that there is a left action on T tangent vectors and right action on S tangent vectors. Then it's possible. And T tangent vectors, which are left invariant with respect to left action, are they form a finite rank vector bundle over M, and this is called with the standard Lie bracket, which is descent from the bracket of vector fields, and this is called the Lie algebroid, E of G. We have such a vector field, then we restrict to the identity section, we obtain a vector bundle over M. And now the structure map is simply DS. So the anchor map is simply DS. So that's here in the pictures, one can see how it looks like. Okay, so like for Lie algebroids, we can do the same for Lie groupoids. We can construct jet groupoids, but instead of sections, how for Lie algebroid, we can construct the bundle of first jets, or K jets, and then it turned out to be a Lie algebroid with a unique extension of a Lie algebroid structure. We can do the same for a groupoid, but instead of sections, we should look at bisections. So the local submanifolds, local bisections, local submanifolds of G, which are diffeomorphically diffeomorphically projected by use of both S and T. So the sections, local sections with respect to both maps S and T. And then if you look at the first jets, it turns out to be a groupoid itself, with the natural projection pi1, 0 from jet 1 of G to G, which is a Lie groupoid morphism. So for instance, that's one of the motivating examples of G is a pair groupoid. So G itself is the product of M cross M, and the target is the first projection, the source is the another projection, and the composition is also the map from S cross M M to M cross M, where the source of one equals to the target of another one. Just we forget about the middle term. So it's called a pair groupoid. And if you look at the first jet, we obtain so the local bisections now in one-to-one correspondence with local diffeomorphisms of M. And then the groupoid of first jets is the groupoid of first jets of local diffeomorphisms of M. So this is related to pseudo groups, of course. Now the Lie algebroid of jet 1 of G equals to jet 1 of E. So the Lie algebroid of the first jet algebroid of E. And the same is true for K jets of local bisections and the infinite jets of local bisections. The Lie algebroid of jet K of G is the same, is jet K of E, and the Lie algebroid of jet infinity of G calligraphic is jet infinity of E. Actually, once I didn't know that. Of course I knew that it was a folkloric fact, but then I wrote a proof in the paper because I couldn't find. But it turned out that there was a proof of this fact in one of the papers in the 70s where people interested in the equations. In some Brazilian journal, so not in English, so it was hard to find it. But still, the proof existed for many years before. The proof of this fact that a Lie algebroid of jet groupoid is a jet algebroid. So, for instance, the interpretation for the first jet groupoid is also is simple. So we, as usual, we can define first jets of submanifolds with the Grassmannian of the subspaces of tangent of the corresponding dimension. And here the requirement that these subspaces may not intersect, so the intersection with Vt and Vs must be 0, so they should be projectable to Tm, to the base manifold. So how it's written here, so the element of jet 1 of G calligraphic is a subspace of the tangent to the element of G, such that it's projectable, isomorphically projectable by d differential of S and differential of T to the tangent of M. So it means that well, so it's open subset of the Grassmannian of subspaces of tangent of G of the same dimension, of the base manifold, of course. So by Cartan-Lie algebroid, we mean a Lie groupoid together with a section from G to jet 1 of G, which is a Lie groupoid morphism. So this is a generalization of the definition of Cartan-Lie algebroid by use of the Bott sequence. How to view such a section? So it means that for each element of G calligraphic, to each element of G calligraphic, we associate some element of G jet 1 of third jets of local bisections over the same point, that we know that these are in one-to-one correspondence with subspaces of the same dimension of the base manifold of TG at the same point, which may not intersect with vertical T-vertical and S-vertical vector field. So in fact, such a section is nothing but a distribution of by subspaces of the same dimension of the base manifold. And then if this section from G to J1 of G is a Lie groupoid morphisms, one can show that this is in one-to-one correspondence with multiplicative distributions. So those distributions for which the map, the multiplication of G crossover MG to G is a morphism. So there, just again, this sort of structures is related to Lie equations, but first it was formalized in such a way by Blaum in the paper Cartan connections to Lie groupoids and the integrability. And then also in more general setting, it was used by Kreinig and his students. It was called multiplicative forms and Spencer operators. They actually did more. They tried to reformulate all the theory of Lie equations by use of groupoids and multiplicative structures in groupoids. But what is written here about Cartan-Lie groupoids, of course, it's a particular case. It's much easier to understand. So in contrast to Lie groups, the left and right translation is not well defined. It's also only well defined on T vertical and S vertical vectors respectively. So the left is defined on T vertical, right is defined on S vertical vectors. But whenever we choose a section or multiplicative distribution by subspaces which are projectable to M by use of S and T, then such a structure becomes left and right translations become well defined on the whole TG. And this is the generalization of the fact that whenever we have a Cartan connection, then E, the Lie algebroid, is acting on both Tm and on itself viewed as a vector bundle. So this just a picture which illustrates how it looks like. It means that the Cartan-Lie groupoid acts on Tm in particular, and the infinitesimal counterpart of this section is the E connection. And the Cartan-Lie groupoid acts on E on the Lie algebroid, and again, the infinitesimal part is the connection E connection nabla alpha, which was defined before. Now, let me try to relate. Okay, finally, this will I will end up now with all geometry and come slowly to mathematical physics. Let me relate all these structures with Riemannian matrices on groupoids. So people tried to do this a long time ago. For instance, in '89, there was the first paper about Riemannian groupoids. And the people considered groupoids with a Riemannian structure. And they say that the Riemannian groupoid is both source and target maps are Riemannian submersions. And the inversion is an isometry. Inversion means the inverse map. This actually, it's such a structure. It's easy to understand what it is, but it's not very useful. I mean, it's difficult to apply this somewhere. I know, just some sort of definition. It's too broad, I would say. There's an example of such a groupoid. So, for instance, for any Riemannian manifold M, if you consider the product groupoid M cross M and endowed with the product metric, then this is a Riemannian groupoid in the above sense. Too many of them, unfortunately. And now how to relate all the structures in the groupoid with Riemannian metrics. So the definition is easy. So we say that the Cartan-Lie groupoid is called a Riemannian Cartan-Lie groupoid if the metric is bi-invariant. As I said, a Cartan-Lie, in the case of a Cartan-Lie groupoid, Cartan connectional, one can say bi-connectional on Lie groupoid, there is an action on the tangent, and thus there is an action on metrics in particular. And this metric is bi-invariant, then invariant under inversion map, then it's called a Riemannian Cartan-Lie groupoid. So this is a generalization of a Riemannian metric, bi-invariant Riemannian metric on a Lie group. And we can do the same for Lie algebroids. Suppose E is a Cartan-Lie algebroid over M, G is a metric on the base manifold M, kappa is non-degenerate fiber-wise metric on E. And let's assume that both G and Car are invariant under the kappa are invariant under the actions with respect to the Cartan connection, nabla tau and nabla alpha respectively. Then we call this a quadratic Lie algebroid. So it's a generalization of quadratic Lie algebra for which the metric on the Lie algebra, the scalar product on the Lie algebra is invariant with respect to the Lie bracket. So that's how we can do this for a Lie algebroid. But then for that we need some auxiliary structure, namely the Cartan connection. Otherwise, it's hard to say what does it mean being invariant. So in particular, if both metrics are positive, definitely, then we say that it's a positive quadratic Lie algebroid. Now, just a good question, how to relate quadratic Lie algebroids and Riemannian Cartan-Lie groupoids. So what we know that if we have a Lie algebra, which is quadratic Lie algebra, so there's invariant metric on it, invariant scalar product, which is not necessarily positive, then we immediately obtain a bi-invariant metric on the corresponding Lie group by use of the translations. And the result does not depend on the translations, we know, because it's invariant. Now, how can we do this here? Yes, and in this picture with the Lie group and Lie algebra, if we extend a metric on the Lie algebra Lie algebra by use of left and right translation. Then if you restrict this to the tangent at the identity of the Lie group, we recover the original metric. And now if we try to do this, the following here. So suppose we have a quadratic structure on E, JK, then how it's related to bi-invariant matrix on TG. So in both cases, G is Cartan-Lie and E is also Cartan-Lie, and E is a Lie algebroid of G, and one Cartan structure is obtained out of another one. Then, okay, so whenever we have eta, a bi-invariant metric on TG, first we can restrict this to the identity section of the groupoid, and we obtain a metric on M. Second, we restrict to T fibers, and we obtain a metric on E. So it means that we can always get the couple of metrics G and kappa on M, Tm, and E respectively by use of bi-invariant metrics on TG. Can we do in the opposite direction? Suppose we have a couple of G and kappa, which are in this case positive quadratic structures on E and Tm and E respectively. Can we obtain eta, a positive metric bi-invariant metric on TG, such that the restriction gives G and kappa respectively? So, and then it turns out that this is indeed possible. It was kind of nice observation because it was not easy to understand. It turned out that some linear equation can be solved, which was surprisingly. But then we found some estimates. So it can be done if 1 minus rho, the square root of 1 minus rho star with the anchor map, rho with the anchor map of E is smooth. So there's some kind of funny property. No one believed that this is the case, but this is true. Okay, so we found, actually, we proved this theorem, which is more complicated than usual, but it's a generalization of the theorem that every quadratic Lie algebra gives rise to a Lie group with a bi-invariant metric. Okay, and this was written in our paper in Letters in Mathematical Physics, the bound integration of quadratic Lie algebroids to Riemannian Cartan-Lie groupoids. The other stuff, the original Killing Lie algebroid, they appeared in the paper Gauging Without Initial Symmetries. And we've shown that it's possible to gauge the standard sigma model by use not only Killing vectors, it was supposed before, but also by use of non-Killing direction whenever we have a Killing Lie algebroid. And this turned out to be again a gauge theorem. And the second paper here in the Reviews Mathematical Physics, we proved a lot about Cartan structures on Lie algebroids and the relation to mathematical physics. And then the third paper, which is called Curving Yang-Mills-Higgs gauge theories, and actually it was the motivation for all these structures. And let me use, I don't have too much time, but it was assumed to be like that because there are too many details which everyone can look at the presentation file or the paper if one likes it. So now I will explain how this appears in mathematical physics. So so the original idea was to try to generalize, try to extend the notion of Yang-Mills-Higgs gauge theories in the direction where we have not a Lie algebra but a Lie algebroid. And it's, of course, it's much more general because in nature, not all symmetries, not all the structure functions necessarily structure constants. So that it's much more general to expect Lie algebroids rather than Lie algebras. So we have the following data. So sigma is a d-dimensional Lorentzian manifold. Mg is a Riemannian manifold. So sigma is the source, Mg is the target. E rho is a Lie algebroid over M together with the fiber metric kappa. So all the reminds the previous structures. And B is an E valued to form an M. Now we define fields of the curved Yang-Mills-Higgs gauge theory. We call this curved because it's not, in this non-curved would mean just the usual Yang-Mills, and curved means that we have some Lie algebroid and the connection which is not necessarily flat on it. So that the Higgs fields are smooth maps, X, I call this X from sigma to M. In usual Higgs theory, M is normally a vector bundle, but this can be also nonlinear. The gauge fields are sections of X star E tensor T star sigma, or we can view all together as bundle maps from Tm to E, or using the graded manifolds language, it's a morphism of graded manifolds of T shifted by 1 sigma to E shifted by 1. The next structure is a vector bundle connection on E, which is gives us the connection and the torsion in the formula as above, as I already explained at the beginning. And then we can define two tensors by use of this connection. The first one can be defined without the connection. This is dx capital, which is dx minus rho of A. So this does not depend on the choice of a connection, but the other one depends. So that two, it's sort of generalization. The first one would be in the usual language of Cartan, usual language on Yang-Mills. This would be the covariant derivative, and second one would be the curvature. So that's how it's defined. But okay, that's kind of easier to see if one looks carefully at the definition. Then there is, as I said, there is a theorem of Weintraub that Lie algebroid structures are in one-to-one correspondence with graded supermanifolds of degree 1 together with homological vector fields. And actually, I hope Iosif Simonovich is not sleeping, because first I learned about this sort of differentials from his paper. He constructed differential on Poisson manifolds.
I don't see.
Yeah, I think this was you who first constructed differential on Poisson manifolds, right? And then it was probably generalized later. It's a particular case of Lie algebroid differentials, and particularly later it was generalized by whom? By Lichnerovich, I guess. So anyway, so suppose we have a bundle map from T sigma to E, and we can ask whenever if it's a chain map or not with respect to these Q structures. And then if this is the case, so it's a chain map, or in other words, it's a Lie algebroid morphism, if and only if dx and f vanish altogether. In fact, these sort of structures, I mean, Q manifolds, it's a nice language to describe topological theories. For instance, there was a paper famous paper of Alexander Schwarz-Zaboronsky from 1995, where they generalized, not generally, they explained all known topological field theories by use of Q manifolds. But in this case, the equations of motions are not necessarily Q morphisms, they're chain maps. But in the field, in the case of Yang-Mills, as we perfectly know, the solutions to the equations of motion not necessarily flat connections. The curvature can be non-zero, and that for that reason we so in our case also true. So we work with the curvature, with the generalization of the curvature. Here it's f telegraphic, and actually splits into two parts whenever we have a connection nabla, so both T capital X and F. So, and T sigma to E is a Lie algebroid morphism if and only if both dx and f vanish together. And then we can construct now an action. So an action looks as follows. It's a sum of two actions. So the first one is the Higgs action. It's a half of the integral over sigma g dx star dx, where star is the Hodge operator. And the second one is the Yang-Mills, a curved Yang-Mills type of action. So the first one is can be constructed without connection, but the second one, for the second one we need a connection, and moreover we need the B field B. And G is an expression which is of the form F, and F is defined as above, plus B applied to dx twice. Well, and what is nice about that? First of all, if G is a Lie algebra, and V is a unitary representation of G, and E is G cross V, the corresponding action Lie algebroid together with the canonical flat Cartan connection. Canonical means all elements of G are flat sections. Then the curved Yang-Mills-Higgs is nothing but the usual Yang-Mills-Higgs field. And for that, we need to write B equals to 0, this usual Yang-Mills-Higgs action. But this is more general. And then we can construct, I will skip it because it's, well, it's not it's a certain formula which, of course, it has some invariant meaning, but I will skip the definition here. It's written in the presentation file. But the idea that the final result is the following. So as curved Yang-Mills-Higgs is gauge invariant if and only if the following conditions are holding. So first of all, nabla is a Cartan connection, so S equals to 0. Second, the both second and third, the both metrics G on Tm and kappa on E are preserved by the corresponding actions of the Lie algebroid. And this 1, 2, 3, as we see, if someone remembers the definition from the previous 15 minutes, 20 minutes, it was a Cartan-Lie algebroid, a quadratic Cartan-Lie algebroid. And the first condition is somewhat more complicated. So there's cosmological type of conditions, and one can explain how it's, what are the cosmological meaning of that. This relates the B form B and the curvature of nabla. So if the curvature of nabla equals to 0, again, we reduce to the classical type of curved Yang-Mills-Higgs. But the importance is that here we do not need to necessarily have a Lie algebra in the game, or flat connection, which is equivalent flat Cartan connection. So here everything can be non-flat, and for that reason we call this curved. So the first 1, 2, 3 are is the definition of a quadratic Cartan-Lie algebroid, which can be integrated to the Cartan-Lie Riemannian groupoid. So it's a Cartan-Lie groupoid with a bi-invariant metric. And the last one is the cosmologically type of property for B. So whenever we have nabla, it defines certain type of complex, and then B turned out to be always a cocycle. And then, yes, it was always a cocycle. And when this is a coboundary, then this property is holding, and then altogether gives rise to a gauge invariant, new type of gauge theory. And here, so the auxiliary to form is not explicitly defined yet. We only know that this must satisfy the fourth equation. It's a mistake. Then the question, of course, is how to find leaf examples of such structures. It turned out to become quite complicated. Here also the end I explained its cosmological property of B, but I do not have too much time to explain it. So there, thank you for attention. That's all.
Okay, Lusha, thanks a lot. Questions?
If anyone is interested, I will, or maybe I should anyway send this, right? So I will send the presentation file. And one can
yes, I hope you will.
Mm-hmm.
So, does anyone has questions or remarks?
The good question, if anyone is still here.
Well, a lot of people are still here.
Because I'm pretty sure that it was maybe not very very common to hear. So there are certain things which are probably not so well known to the audience.
Okay, nevertheless, does anyone have questions, remarks, comments? No. Then thank you very much for participation.
Thank you.
Well, we meet in a week, and our next speaker will be Igor Havkin from
Igor.
Leosh, I think it will be interesting to you at least. And not
yes, only. I guess so.
Okay, thanks a lot.
He was my guest in Vienna.
When?
In Vienna.
Yeah, sure. Yes, yeah. I know. Yes. Okay, thanks a lot again, and see you in a week.